We begin our first lecture in Circuit Theory 2 course by introducing a component which we didn't have time to talk about in Circuit Theory 1, okay? Namely the coupled inductors. The motivation behind studying coupled inductors is this. Okay. So when two or three or four inductors are physically close to one another, okay, are brought close, or they wound on the same core, then their effect upon one another cannot be ignored. So they start affecting each other. Okay, so in that case, we say they become coupled. So, to give a rough idea on the physical situation, suppose that we have this magnetic core, okay, and here we wind the first coil, and here we wind our second coil. So let's label the voltage and current here as V1 and I1, obeying always passive sign convention. And similarly, we label the voltage and current here as V2 and I2. Okay. Now, this physical device we model in 201 as such that the voltage generated here is proportional to the rate of change of the current, okay, and proportional to the constant we call the inductance of the coil, okay, or inductance of the inductor. So V1 equals some constant times dI1 dt. This is our LTI model for this physical device, which is quite accurate for many situations, okay? And likewise, V2 equals some constant times the rate of change of the second current, dI2 dt, okay? Now that in this case, V1, this voltage, depends only on its own current. Likewise, the second voltage depends only on its own current. So when that's the case, we call this situation uncoupled case, okay? And in certain situations, this might be an accurate way to describe the situation, okay? So that this might be enough, okay, for our purpose. But in some cases, the flux generated here affects the flux here in the second coil and vice versa. Therefore, this model becomes inaccurate, and that means we have to modify our model, okay? And that modification is through the so-called coupling terms. So when, for that case, okay, so when this model is no longer sufficient, what we do is we resort to the following, okay? V1 equals L1 dI1 dt, but not only that, also as the coupling term, some constant dI2 dt. Okay? So this is closer to the real situation where voltage in the first coil depends not only on its own current but also the current flowing in the other neighbor coil. And similarly, V2 equals L2 dI2 dt plus the coupling term. One nice thing about the coupling is that it's symmetric in the sense that here we have mu di through dt for the coupling term for the first voltage. For the second voltage, we have the same constant times the rate of change of the first coil's current. Okay, so it's usually well, in certain situations, it's nice to put these two equations into a single matrix equation. So let's do that. Okay. So in matrix form, we have. Okay. So to obtain matrix form, what we do is we stack the voltages and obtain our voltage vector. Okay. And then we stack our currents and obtain the current vector. Note that the currents appear as through their rate of changes. Therefore, what we have is d over dt time derivative of the current vector, I1, I2. Okay, and then these coefficients, okay, determine the matrix, the entries of the matrix that relates this voltage vector to the current vector, or the rate of change of the current vector. Okay. So let's call this V. Okay, this is our voltage vector. Let's call this I. It's our current vector. Okay. And then here we have a vector of size 2. Here we have a vector of size 2. And they are related to one another by this matrix, and that matrix has to be of size 2 by 2. So we have to figure out the 4 entries of that square matrix. That matrix, by the way, is called inductance matrix, and it's labeled by capital F, not surprising. This is our inductance matrix. So let's fill in the entries of the inductance matrix by looking at these two individual equations. Okay, so for V1 we have L1 times the I1 dt plus mu times the I2 dt. Okay, so therefore L1 should appear here, L1 times the I1 dt plus mu times the I2 dt. Okay, this is mu. And for V2 we have L2 times the I2 dt. So here we must have L2 and mu times the I1 dt. Here we have mu. So when written in matrix form, symmetry is, or has become, more visual. Okay. So compactly, therefore, we can write V equals L times the I dt. Okay, note that this looks exactly the same as the scalar inductor equation, but this time it's expressing a more general situation where this is a vector, this too is a vector of the same size, and here we have a matrix, square matrix, that relates this vector to that vector. Okay. So in this expression, or in this matrix equation, the diagonal terms are called the self-inductances. Okay. So L1, L2 are called the self-inductance. Okay. And whereas the off-diagonal terms are called the mutual inductance, or more accurately, their magnitude or their absolute value is called the mutual inductance. So this case can have generalizations for more than 2 inductors, okay, 3, 4, however many is necessary to model the actual physical device. Okay. But one nice thing about all those representations is that the inductance matrix, which always be a square matrix, will be symmetric. Okay, so let's put that down as a remark. Note that the inductance matrix is symmetric. For instance, for 3 coupled inductors, we have something like this. We have the voltage vector, which contains 3 individual voltages corresponding to 3 coils. Okay. Then we have the inductance matrix. We have the rate of change of the current vector. Okay. I1, the current of the first coil whose voltage is V1, I2 whose voltage is V2, and so on. I3. Okay. The diagonal entries of that matrix we call self-inductances. Okay, so L1 is the self-inductance of the first coil, L2 is the first self-inductance of the second coil, and so on. Okay, and the off-diagonal terms, they're called the mutual inductances. Okay, so here we have, let's say, mu1, 2. That's the mutual inductance that represents the relation between the first coil and the second coil. Okay, and the nice thing about our representation is that it has to be symmetric. Okay, so if this is mu1, 2 and this is mu2, 1, those two parameters must be the same. Therefore, we simply call it mu1, 2. This would be mu1, 3, and here we have the same thing, mu1, 3. Here we have mu2, 3, and here we have the same thing, mu2, 3. Okay. Now, the signs of the diagonal terms are positive, but for talking about the passive inductor case, they're positive because we obey we adopt the passive sign convention, okay, which tells us that if you set the direction of the current, the polarity of the voltage is automatically set. So that's that convention we always obey. Okay. How about the signs of the off-diagonal terms, namely mutual inductances as they appear in the matrix? Okay, so to be able to determine that sign, or that sign depends on the orientation of the currents in the actual physical device. Okay, and that orientation in the physical device should somehow be communicated in the circuit diagram. Okay, when we represent this as a diagram in a circuit, and that representation is done through the so-called dot convention. Okay, so we will now talk about, we're going to define and talk about dot convention. Okay. So dot convention means the following. So dots indicate the relative orientation of the coupled inductors. Okay. Well, this explanation is now meaningless at this point because we haven't the diagram. But once I finish the definition, I will put the diagram on and everything will make sense. Okay, so that's indicate relative orientation of the coupled inductors. in the following sense: considering a pair of inductors which are coupled if both currents, I1 and I2, let's say, are leading or entering the coil from the data terminal then the generated fluxes contribute to one another, okay, to each other. And mathematically speaking, that would correspond to the case that the off-diagonal terms will be positive, okay, to each other. So the associated off-diagonal terms of the inductance matrix are positive. Okay, it's very simple. Basically, if they're doing the same thing, leading or entering, doesn't matter, but if they do the same thing, both leave or both enter, then the fluxes contribute to one another, okay, and the off-diagonal terms will be positive. In the other situation, it is doing the opposite thing, one is leaving, the other is entering from the data terminal, then the off-diagonal terms will be negative. It's very simple. Otherwise, they are opposing each other. Okay. And the off-diagonal terms are negative. Now let's apply this definition on some simple cases so that we become familiar with the very useful dot convention. Okay, here's our example. Suppose that we have a coil, we have an inductor, and nearby we have another inductor, and the fluxes affect one another, so we have to model this device as a pair of coupled inductors. Okay. So plus minus V1, and let's call this I1. This is how we label the voltage and current, obeying always passive sign convention, and let's do the same thing here, V2 and I2. And the self-inductances are given to be 3 Henry and 4 Henry, okay? So in the diagram, they're written somewhere close to the coil, so we know that this is the self-inductance of the first coil, this is the self-inductance of the second coil. As for the mutual inductance, it's written through this an arc or an edge with two arrowheads. Okay, so that's the convention. And somewhere close to that arrows, we put the mutual inductance information, which is 2 Henrys. Okay, and then so this is, or these are the self-inductances. Okay, and this is so-called mutual inductance. Okay. With only this amount of information, we cannot determine, okay, whether the fluxes generated in separate coils are contributing to one another or opposing one another. In other words, we know that inductance matrix will have diagonal terms 3 and 4, okay, L1 and L2, but we don't know, we cannot say by just looking at this picture whether the off-diagonal term will be plus minus, plus 2 or minus 2, okay, and for that we need the dots. We need information that's communicated to us by dots. And suppose that the dots are put like this, okay? And now everything that we need is here to model or to write the model of this device. By looking at the dots, we can determine the sign of the off-diagonal terms in the inductance matrix. Okay, so here is the dot for the first coil, here is the dot for the second coil. So I1 is entering, so to speak, from the dot. I2 is entering from the dot also. Therefore, they're doing the same thing. Therefore, the sign of the off-diagonal term will be positive. Okay. So L, therefore, equals, these are the diagonal terms, 3 and 4, the self-inductances, for which we don't need the dots to write, but for the off-diagonal term, we have plus 2 and plus 2. Okay. So in other words, it means that V1 equals 3 times the I1 dt plus 2 times the I2 dt. And V2 equals 2 times the I1 dt, the calc term, plus 4 times the I2 dt. Okay, it's very easy. If this dot were here, in that case, the first current is entering from the terminal, the second current is leaving from the terminal, then this L will be such that the off-diagonal terms will be minus 2's. Now let's go over some simple cases to make ourselves familiar with the dot convention and also coupled inductors. Okay, example. Plus minus V1, I1, I2 plus minus V2, always obeying passive sign convention. 2 Henry, 2 Henry, okay, they are the self-inductances. And then we have mutual inductance given as 1 Henry with dots placed, one here, the other is here. Okay. So that means the inductance matrix equals 2, 2 self-inductances. Then here we have plus minus 1, plus minus 1. So let's figure out whether this is plus or minus. First current is entering from the dotted terminal, second current is leaving from the dotted terminal. Okay. Therefore, they are opposing, the flux are opposing one another, meaning the off-diagonal terms must be negative. Okay. So we have minus and minus. Here's another example. Suppose that we have some arbitrary circuit. Okay. So even though when we draw the circuit, they may look physically far from one another in the actual physical device. They may be coupled, they may be close enough to be coupled. Therefore, still we may have some coupling for the coils that appear far away in the diagram. Okay, because the diagram doesn't tell us much about the physical properties of the device. Only tells us which is connected, which component is connected to which. Okay. So here we have L1 with dot here. Here we have other dot plus minus V1, and here we have plus minus V2. Here we have I2, and here we have the mutual inductance represented by N. So for this pair of coupled inductors, we have the following inductance matrix: L1, L2. The self-inductances appear in the diagonal, and here we have either plus or minus N's. Okay, whether it's plus or minus, we will determine by looking at the dots. I1 is leading from the dotted terminal. I2 is also leading from the dotted terminal. Therefore, we have to have plus N's here. Okay, so it's very simple. Now, let's consider some other examples where coupled inductors are connected in such a way that that four-terminal device becomes a two-terminal device. Okay, and then the question is how to, if possible, model that two-terminal device or a single branch device. Here is our first example. Find the equivalent inductance for the following one port or two-terminal device. L equal where that constant is such that it relates voltage to the rate of change of current. L equivalent, or sometimes it's called L effective inductance. Di dt. Now, this is the statement of the problem or the circuit, and this is the circuit itself. L1, L2. Okay, so this is our four-terminal device, a pair of coupled inductors. And from this four-terminal device, what's being obtained is we obtain the following two-terminal device, okay, by shorting these two separate terminals and making a single node. And then for this new two-terminal device, the labeling for the voltage and current is given as follows. Okay, so it turns out that this component can be represented by a single inductor, or in other words, its voltage and rate of change of current satisfies such a relation, and in that relation, this constant we're calling the equivalent inductance, okay, or the effective inductance for this configuration. So what we're asked to do is to figure out this constant, this parameter L equivalent, in terms of L1, L2, and N. Okay. So for that, because we want to be able to write the terminal equations for our coupled inductors, we have to do some labeling. Okay, so let labeling be following. By labeling, I mean assigning voltages and currents to to the coils. So let this be V1, let this be I1. Okay. And let this voltage be V2, and we have to obey the passive sign convention. Therefore, the current should be directed as such. That's our I2. Okay. And then now we have the labeling. We can write down the model, and then from those equations in the model, we will hopefully obtain this L equivalent. Okay. So let's do that. So what we have is, this V, this voltage equals the sum of voltages in this path. Okay, so we have V1 plus minus, and then we have plus minus V2. Okay, so they're on the same path. Therefore, this by KVL, this voltage V must equal V1 plus V2. Okay. Now, somehow we want to relate this voltage to currents. So for that, let's use the terminal equations for our coupled inductors. So what we have is V1 equals L1 dI1 dt plus or minus n times dI2 dt. Okay, so to determine whether it's plus or minus, we'll get the dots. I1 is entering from the dot terminal. I2 is entering from the dot terminal 2. Therefore, they're doing the same thing. Hence, we have to have n di2 dt. Likewise, V2 equals L2 di2 dt plus n di1 dt. So, therefore, by substituting these V1 and V2 by those expressions, we can express V, the voltage of the overall two-terminal device, in terms of the rate of change of currents. Okay? But we don't need those currents. Well, what we need is we need to express everything in terms of a single current. So that means we have to relate those currents of the coils I1, I2 to the current of our two-terminal device I. And that's easy because this I1 is no other than I, and then I goes in this way, and here we see that it's also I2. Therefore, I1, I2, and I, they're all the same current by KCL. Okay. So I equals I1, and that equals I2. So therefore, first we will write these V1 and V2 in terms of those currents, and we know that all those currents can be expressed in terms of I. Therefore, what we will have is we have V equals something that's only in terms of I. And from that equation, we will be able to pull L equal. So it's very easy to combine all those equations, and we immediately see that V equals L1 plus L2 plus 2N di dt. Okay. So that's the relation between voltage and rate of change of current, and therefore this constant here must be what we're calling L equivalent. L effective or L equivalent equals L1 plus L2 plus 2N. Okay. Now here is a follow-up. Also note that this answer, L equivalent, is independent, must be independent of how we choose the coil voltages and coil currents. Okay, because the physical device doesn't care about how you label it. it's going to do what it has to do. So that's the answer. Now the follow-up question is this. Suppose that the dots were located or situated as such. Okay, now how about this case? Okay. Again, what you're going to do is you're going to do the labeling. V1, V2, I1, I2, and then write down the determinant equations, and from that try to obtain V in terms of the I1 dt. Okay, and no matter how you choose to do the labeling, you will obtain the same answer, and that answer must be, well, maybe some of you directly see it without any computations, but basically this L1 plus L2 minus 2m. Okay, so that would be a nice exercise to figure out. Okay, here's another exercise. Suppose that we have, again, a pair of coupled inductors. Okay. This time, let's give some numerical values. This is 300, 400 self-inductances, and the mutual inductance with dots placed as such is 2 Henry. And then, from this device, what you do is you obtain a 3-terminal device. Right now it has 4 terminals, and then by shorting these 2 terminals, okay, you obtain a 3-terminal device. Let's call the nodes as A, B, and C. This is also C, okay, because they're shorted. Now let's do the labeling. This is B1, I1. This is I2, and this is, let's call B2. Okay. Suppose that this 3-terminal device has the same voltage current characteristics as the following 3-terminal device. Again, a device of inductors, but this time the inductors are uncoupled. Okay. And let's call them L1, L2, and L3. Okay, let's call them L1, L2, L3, and let this voltage be V1, let this voltage be V2, this current I1, this current I2. Okay. Now it turns out that there is such an equivalent if you choose the inductance values in this so-called T connection properly. And the question that would be a nice exercise to answer is the following. Suppose that these two 3-terminal devices are equivalent. So let's do the proper labeling. This is A, this is B, and this is the terminal C. And then for that equivalence to hold, what should the inductances here be? Here, inductors are uncoupled. Okay, so we don't have any dots anywhere here uncoupled. Of course, we have through writing terminal equations here and terminal equations here, it's very easy to figure out what should L1, L2, and L3 be. But to talk about equivalence in the proper sense, because we're talking about a dynamic element, we also have to be careful about, it's not what's asked, but we have to be careful about the initial conditions, okay, in this case, the initial conditions. So clearly, to talk about exact equivalence, whatever the initial currents here, I10 and I20, we must have the same initial currents here, I10 and I20. plus the carefully chosen inductance values, we would have the true equivalence between those two dynamic three-terminal devices. Okay, so the exercise is find L1, L2, L3 inductances of the uncoupled inductors in the second case. Okay. Now, let's see one further example. This time we have three coupled inductors. Connected in this series fashion. Okay. The self-inductances are L1, L2, and L3. Okay. Then we have three mutual inductances. One relating first to second coil, the other is relating first to third coil, and the third is relating second to third coil. Okay, and each of those mutual inductances require a pair of dots. Okay, so what we have here is this is N1, 2 with dots placed as such, and then we have N2, 3 dots placed as such, and finally we have N1, 3, where dots are placed in the shown positions. Okay. Now we have therefore a triplet of inductors, and they're coupled. Okay. And the dots and mutual inductances are given as shown. And from this 3 or 6 terminal device, through this connection you obtain a 2 terminal device, and you label its voltage and current as follows. Okay? Now it turns out that this 2 terminal device can be represented by a single inductor, meaning that V equals some constant times the rate of change of the current. And now what we're asked is, we're asked for that constant. So what's L equivalent, which appears in the equation V equals L equivalent times di dt. Okay. So again, to obtain that equation, or to obtain L equivalent, what we need is we need to use the terminal equations for the coupled inductors. To be able to use the terminal equations for the coupled inductors, we need some voltages and currents, okay, for those coils. So that means we have to do labeling. So let's go ahead and do labeling as follows. But note that this answer, whatever it will turn out, should be independent of how you do the labeling, how you choose the polarity of the voltage and direction of currents. Okay. So since that's the case, let's choose the one that seems to be easiest to work with. Okay, so let's call this voltage V1. Let's call this voltage V2, voltage of the second coil. And finally, let's call this voltage V3, voltage of the third coil. And by passive sign convention. This is I1, this is I2, and this is I3. The nice thing is they're all series, so I1 equals I2 equals I3, and that equals I. Okay? So we don't have to label the currents separately because it's already completed diagram. Okay. So to obtain L equivalent, let's again start from KVL. Okay. So this voltage, the voltage that appears across this pair of terminals, equals by KVL clearly V1 plus V2 plus V3, the sum of voltages of the individual coils. V1 plus V2 plus V3. So what's V1? Okay. So V1 equals L1 dI1. Okay. So here D is our dt notation. Okay, or dI is di dt. Okay, so we're using the capital D notation to denote rate of change with respect to time. So we have L1 dI1 plus minus N12 dI2. Let me write it. I1 plus N plus minus N13 dI3. Okay? So by KCL, we said that all the currents I1, I2, I3, they're equal to I, therefore we can get rid of these subscripts immediately. And then we have to determine whether this is plus or minus, and likewise whether this is plus or minus. For that, what we have to do, we have to look at the dots. Okay? So to determine this sign, here we have, okay, so this was I1 and this was I2. Here, I1 is entering from the dotted terminal, I2 is also entering from the dotted terminal, therefore this should be a plus. The fluxes are contributing to one another. Okay? And to determine the sign of this N13, we have to look at the dots, this and that. Okay? Here we have I1, and here we have I3. I1 is entering from dotted terminal, I3 is leaving from the dotted terminal, therefore the sign of this must be minus. Okay. Now similarly, we can write down expressions for V2 and V3. So let me write it down. di plus N12 di minus N23 di, and V3 is L3 di minus N13 di minus N23 di. Okay. Then once those term equations are written down in terms of I, all we have to do is just sum them up, okay? And then collect the terms, and what we will have is, we will have V equals something times di, and that something is the effective inductance. So let's finish the example by writing down the answer. So we have, therefore, V equals, we're summing all those three equations. On the left hand side we have V1 plus V2 plus V3, which is no other than V. And on the right hand side we will have something times di. And that something turns out to be L1 plus L2 plus L3 plus 2N12 minus 2N13 minus 2N23 times di. Therefore, the effective inductance or the equivalent inductance must be this chunk here. L1 plus L2 plus L3 plus 2N minus 2N13 minus 2N